In the previous lectures of the series on QFT a la Weinberg, I have talked about the effect of Parity transformations on 4-momentum eigenstates for both massive and massless single particle states. We had confined ourselves, however, to just translations and Lorenz transformations which were connected continuously to the identity, that is, proper orthochronous Lorenz transformations. In this section, we are going to talk about discrete Lorentz transformations. In particular, about the two specific cases, space inversion and time reversal. Let me remind you that any homogeneous Lorentz transformation, that is, of course, a Parity transformation without the translation part, is either proper and orthochronous. Once again, let me remind you that this means the determinant of the corresponding matrix is +1 and the 0,0th element of the matrix is greater than or equal to +1. So this is one possibility. Or the other possibility is that the homogeneous Lorentz transformation is a product of a proper orthochronous transformation with either space inversion curly p or time reversal curly t or the product curly p times curly t. Here curly p and curly t are the following two specific Lorentz transformations. The elements of curly p are the following: 1, 0, 0, 0, which essentially tells you that the time does not change under space inversion. 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, which essentially tells you that under a space inversion, x goes to minus x, y goes to minus y, and z goes to minus z. This is a Lorentz transformation simply because, like a genuine Lorentz transformation, like all Lorentz transformations, it keeps the interval delta t square minus delta x square minus delta y square minus delta z square invariant. Time reversal, on the other hand, is a Lorentz transformation which changes the sign of the time t goes to minus t while leaving x, y and z intact, and hence its matrix elements are given by minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0 and 1. Of course, the product curly p times curly t would have minus 1s right down the diagonal and zeros everywhere else. So curly p curly t is actually negative of the identity. Now all of these are genuine Lorentz transformations, and if you combine them with a proper orthochronous Lorentz transformation, you are going to get a Lorentz transformation which is not proper and orthochronous. By the way, let me point out that the notation that I have adopted here is very similar to what Weinberg has done. That's what I'm trying to follow throughout, except for one very important thing. I've already stated that before several times during the course of these lectures, but let me stress that once again. Weinberg orders his space-time indices in the following manner. He puts 1, 2, 3 first, then comes 0. Whereas I have used a more standard 0, 1, 2, 3, which is why my curly p and curly t matrices look slightly different from Weinberg's curly p and curly t matrices. However, the content, of course, is exactly the same. We had earlier studied the composition rule for Parity transformations. That is a Parity transformation with a Lorentz transformation lambda bar and translation a bar times another with a Lorentz transformation lambda and translation a would combine to give you a Parity transformation whose Lorentz transformation part is simply the product lambda bar lambda, while the translation part is slightly more complicated. It's lambda bar times a plus a bar. This composition rule is what we pointed out as proof of the semi-direct product structure of the Parity group. Now, from the derivation of this, it should be obvious that this would work not only for proper orthochronous Lorentz transformations, it would also work when either lambda or lambda bar or both involves factors of curly p or curly t or curly p times curly t. That is, it would work no matter whether the corresponding Lorentz transformations are proper orthochronous or not. Now, what was considered self-evident till the 1960s is that this will also work for the operators that act on Hilbert space. Remember, corresponding to every Poincare transformation lambda comma A, you would expect there to be a operator u of lambda comma A, and you would expect the following composition rule to work. U of lambda bar A bar times u of lambda A should be equal to u of lambda bar lambda, comma lambda bar A plus A bar. In particular, what was considered to be obvious is that if you consider purely a Poincare transformation which has no translation, and the Lorenz transformation part is just space inversion or time reversal, you will also have a corresponding unitary or anti-unitary operator for that. Remember, we had already stated before, although we have not proven it yet, we will later, the statement of Wigner's theorem that any symmetry operation can be represented by the action on Hilbert space vectors by either a unitary linear operator or an antilinear anti-unitary operator. Now, what we are claiming here is the following. We are claiming that corresponding to space inversion and time reversal, these two discrete Lorentz transformations, there exist unitary operators, capital P and capital T, which capture the action on Hilbert space vectors. So capital P is nothing but u curly P0, capital T is nothing but u curly T0. Note that the existence of such operators was taken to be self-evident, at least at one time, and it was only later that experiments forced us to the conclusion that for some kinds of physical systems, such operators may simply not exist, or in general they may exist only as an approximation but not as a perfect picture of the way the world is. Let us go ahead, however, for the time being with the idea that such operators really exist. Now, from the composition rule for Poincare transformations, you can easily show, as we have done before, the following. Lambda bar A bar times lambda A times the inverse of lambda bar A bar. This particular Poincare transformation happens to be one corresponding to a Lorenz transformation given by lambda bar lambda bar inverse, and a translation given by lambda bar A plus identity minus lambda bar inverse acting on A bar. Now, while this may sound a bit complicated if I just state it out all at once, it's pretty easy to verify this starting from the basic composition rule that we had just written down a while ago. Now, in particular, at the level of Lorenz transformations or Poincare transformations, if you replace lambda bar A bar by curly P comma 0, you immediately end up with the result that curly P comma 0 lambda A curly P comma 0 inverse is simply curly P lambda curly P inverse comma curly P A. And very similarly, you can show that curly T comma 0 times lambda comma A times curly T comma 0 inverse has a very similar expression as curly T lambda curly T inverse comma curly T A. Now, this is obvious from the result that I have written down in green here. All you have to do is put A bar equal to 0 and substitute in place of lambda bar either curly P or curly T, and you're going to get this result. Now, this is a perfectly good result at the level of Poincare transformations combining with each other. However, the assumption that we have made that there are unitary or anti-unitary operators acting on Hilbert space which mimic this transformation rule leads us to the following conclusion. The corresponding operator version will be capital P, which stands for u of curly P comma 0, times u of lambda comma A times capital P inverse is going to be equal to u curly P lambda curly P inverse comma curly P A. A similar result would work for the time reversal operator capital T. Capital T u lambda comma A capital T inverse would be u curly T lambda curly T inverse comma curly T A. Now, as I have been saying, this was taken to be self-evident. The existence of capital P and capital T and the fact that they combine in this particular manner was taken to be self-evident in the early 1960s. In 1956 and 57, Madame Wu carried out a series of experiments. She had theoretical inputs from T.D. Lee and C.N. Yang, and with the help of that, she managed to show that the existence of capital P is really an approximation. There are physical systems, in particular, systems which take part in the weak interaction, for which an exact operator capital P simply cannot exist. Existence of capital P would be inconsistent with the experimental observations that were being made. We are going to discuss this in some great detail later on when we talk about the consequences of the existence of these operators, capital P and capital T, as far as experimental results are concerned. But for the time being, let me point out that the existence of capital P is exactly what we mean when we say parity is conserved, or that there is something called parity symmetry or space inversion symmetry in a system, and weak interactions do not have that symmetry. Time reversal stuck around for a while, but in 1964, physicists obtained indirect evidence that time reversal symmetry is violated as well. So, the existence of the operator capital T is also now known not to be an exact result for all systems, but only approximately valid in the world at large. Be that as it may, in the rest of this section, we are going to assume that such operators capital P and capital T actually exist, and the composition rule P U lambda A P inverse is given by U curly P lambda curly P inverse comma curly P A, and a corresponding similar rule for capital T, both work. Now, let us explore the consequences of this happening. In other words, we are trying to explore what would happen if parity and time reversal were exact symmetries of the universe. Of course, we know that they aren't, but we can still use them to get a very good approximation of the way the universe behaves, and for interactions for which capital P and capital T are actually exact symmetries, for them, what I'm going to say works perfectly without any modifications. Now, what we are going to do next is we are going to assume that in place of this U lambda A, in place of this Poisson transformation parameterized by Lorenz transformation lambda and translation A, we consider the special case when we have an infinitesimal transformation. In other words, lambda is infinitesimally close to the identity, so lambda mu nu is the identity matrix delta mu nu plus a small correction term omega mu nu, and translation A mu is also infinitesimally small, and written epsilon mu. We had earlier seen that in order that lambda mu nu be a Lorenz transformation, omega mu nu must satisfy the following relation. It must be completely antisymmetric in the indices when written with two lower indices. And we had also argued before that under such a Poisson transformation, the corresponding operator U acting on the Hilbert space, U of identity plus omega comma epsilon, will be very, very close to the identity operator, and you can expand this out in the parameters omega and epsilon, which are infinitesimally small, and to first order in omega and epsilon, you will get identity plus I by 2 omega rho sigma j rho sigma minus I epsilon rho p rho, where j rho sigma and p rho are the generators of Lorenz transformations and translations respectively. So starting from this rule, what we see is P times U identity plus omega comma epsilon P inverse must be given by U identity curly P identity curly P inverse is of course just the identity plus curly P omega curly P inverse plus, and the translation where of course the infinitesimal transformation where curly P, the parity matrix, acts on the translation epsilon. Now writing out the infinitesimally close to identity operator U in this particular form gives us P times identity plus I by 2 omega rho sigma j rho sigma minus I epsilon rho p rho times P inverse must be equal to identity plus I by 2 curly P omega curly P inverse. This matrix is mu nuth element times J mu nu minus I curly P epsilon, this column vector's mu nuth element times P mu. And in order to proceed further, what we will need is an expression for curly P omega curly P inverse as mu nuth element. There is something which we have shown earlier. So we are just going to use this result that curly P omega curly P inverse as mu nuth element is curly P mu lower rho upper times curly P lower nu upper sigma times omega rho sigma. And a similar but simpler expression is there for curly P times epsilon's mu nuth element. We just use that, plug it into the expression, and it takes a very little amount of work to compare both sides, where you have to be careful about anti-symmetrizing first, which in this case, thankfully, is taken care of already, at least as far as the omega rho sigma coefficients are concerned. And you end up with the following two relations. Capital P I J rho sigma capital P inverse. Here capital P, remember, is the operator corresponding to the space inversion acting on the Hilbert space, the so-called parity operator, is given by I curly P mu rho curly P nu sigma J mu nu. Capital P I P rho capital P inverse is I curly P mu rho capital P mu. I hope you will not confuse the capital P, which stands for the parity operator, with capital P rho or capital P mu, which are the rhoth or muth components of the form momentum. Although I am using the same letter capital P for both of them, and I don't really have good enough calligraphy to be able to write capital P in a sufficiently different font so that you can distinguish the two from that, I would just point out that capital P, the parity operator, has no indices, and the capital P which has indices like capital P rho or capital P mu must be components of the form momentum. So we are just going to use this notation. A very similar calculation carried out with capital T instead of capital P would give us very similar conclusions. Capital T I J rho sigma capital T inverse is I curly T mu rho curly T nu sigma J mu nu. I, and then capital T I P rho T inverse is I times curly T mu rho P mu. Now, you must have noticed that I have not cancelled out the i's on the two sides, and there is a very good reason for that. At this point, I am not so sure whether the operators capital P and capital T are unitary or anti-unitary. Remember, Wigner's theorem guarantees that symmetry operations can be represented by either unitary linear or anti-unitary antilinear operators. And we had argued earlier that operators which are connected continuously to the identity, like the operators corresponding to the continuous proper orthochronous Lorenz transformations, must be unitary because they start at the identity, which is a unitary operator, and can only change continuously from there. On the other hand, capital P and capital T correspond to space inversion and time reversal respectively. These are discrete transformations which are not continuously connected to the identity. There is no parameter which you can tune continuously so that you will smoothly change from the identity operation to either curly P or curly T. So neither capital P nor capital T is guaranteed by the arguments that we have given so far to be unitary. It's possible that they may be anti-unitary also. In other words, the I, which is multiplying the omega rho sigma J rho sigma or the epsilon rho P rho, may not necessarily come out unchanged from capital P or capital T. We have to be open to the possibility that either capital P or capital T or both of them may end up being anti-unitary, in which case bringing the I out would actually change the sign of it. It would change it to minus I. So now we have to make a choice. Is capital P a unitary operator or an anti-unitary operator? Also, we have to make a similar choice about capital T. And as we will see now, this choice is really rather easy to make. To make the choice for capital P, let us start with this particular equation and look at the particular version for this equation for rho equals 0. So what we have is P0, P inverse, has to be equal to I times curly P's mu 0th element times capital P mu, of course summed over mu. But remember, curly P is a diagonal matrix, so the only non-zero element of the type curly P mu 0 is curly P 0 0. So this sum essentially becomes just one term, I curly P 0 0 times P 0. And since curly P 0 0 is 1, this is just I P 0. Now the reason why I have focused on rho equal to 0, of course, is the fact that capital P0 is none other than the Hamiltonian capital H. So this translates to the following: capital P times IH times capital P inverse is equal to IH. Now, as we have already said, we have two options. Capital P could be anti-unitary or unitary. If P were anti-unitary, it would have to be anti-linear as well. So this I will come out of P as minus I. So you will get minus I P H P inverse is IH. And now we can cancel out the I to get P H P inverse is minus H. Now what this implies is that for each energy eigenvalue E, there will have to be another energy eigenvalue minus E. To see that, all you have to do is look at the following. If psi is an energy eigenstate with energy E, then P psi, well, P psi is a state on which H acts to give you the following. It gives you P inverse HP psi times P on the left. All I've done is put in PP inverse here. Sorry, I cramped this up a bit, which is of course nothing but the identity. Now, if PHP inverse is minus H, it's easy to see that this implies that P inverse HP is also minus H. So this thing is minus H. So you get minus E times psi from this, and since E is a number, it comes out, you end up with minus E times P psi. So if psi happens to be an energy eigenstate with eigenvalue E, P psi has to be an energy eigenstate with eigenvalue minus E. So all energy eigenvalues would have to occur in pairs, plus E and minus E. And in particular, for every positive energy eigenvalue, every energy higher than that of the vacuum, you would also get a negative energy eigenvalue, an energy lower than that of the vacuum. Now we do not have such energies below the vacuum energy. Also, since most systems have no upper bounds on their energies, this would also imply that the systems would have no lower bounds, and that would be a disaster as far as the stability of the system is concerned. So we have to give up this idea that P is an anti-unitary operator. On the other hand, if P is a unitary operator, then P IH P inverse would simply be IH P H inverse, and this would simply tell you that H and P commute. So a similar argument, like the one that I've just made a while ago, would tell you that psi and P psi would have to correspond to the same energy E. Barring degeneracies, that would actually mean that psi and P psi are multiples of each other. A very similar argument can be made for the time reversal operator, starting from this relationship, capital T I P rho T inverse is I curly T mu rho P mu. Again, looking at the case where rho is 0, I get capital T I P0 T inverse is I times curly T mu 0 P mu, sum over mu of course, and once again curly T is a diagonal matrix. This gives you only one term, curly T 0 0 P 0, and since curly T 0 0 is minus 1, it gives you minus IP0. So the relationship for the time reversal operator becomes T IH T inverse is minus H. Now, if T were unitary, the I would have just come out from the left hand side. and would have cancelled the I, which is here. I forgot to write the I here. And therefore, you would end up with TH T inverse is minus H. And this would lead to exactly the same problem that the parity operator being anti-unitary would have. In other words, if T were a linear unitary operator, I would have ended up with pairs of energy eigenvalues plus E and minus E, leading to situations where there are negative energy eigenvalues of energy below the vacuum energy, also an unstable system because there would be no lower bound on the energies. So in order to ensure that such a problem does not arise, capital T has to be anti-unitary. So our conclusion is the following. The parity operator, if it exists, that is, if parity is a good symmetry of the system, then it has to be a linear unitary operator, whereas the time reversal operator, once again, if it exists, has to be an anti-unitary and antilinear operator. Given this conclusion, we can now rewrite the transformation equations for angular momentum and momentum components under parity and time reversal simply by cancelling out the I as appropriate. Remember, for capital T, which is an anti-unitary operator, the I comes out from inside in the form of minus I, and cancelling with the I on the other side leaves you with a minus sign. Which is why capital P J rho sigma capital P inverse is curly P mu rho curly P nu sigma J mu nu, whereas capital T J rho sigma capital T inverse is minus curly T mu rho curly T nu sigma J mu nu. And a similar minus sign occurs for momentum components as well for the time reversal case. Now this equation may look more familiar and make more sense to us if instead of thinking about the Lorenz transformation generators and the 4 momentum components, we broke this up into angular momentum, boost, Hamiltonian and the 3 momentum. And that's pretty easy to do. All you have to do is remember that the purely spatial index version for capital J ij's are angular momentum generators. Capital J 0i's are boost generators. Capital P0, of course, is the Hamiltonian, the one which we have already met. And capital Pi, the spatial components, are nothing but the 3 momentum vector components. So now let us take a look at what these equations say about the way in which these familiar operators transform under parity and time reversal. Let's take a look first at angular momentum, and let's pick a particular component, J23, which is the first component of the angular momentum, J lower 1. So from this equation, P J23 P inverse will simply be curly P mu 2 nu 3 J mu nu, sum over mu and nu, of course. Once again, the fact that curly P happens to be a diagonal matrix makes this expression a lot simpler than it usually is. The only non-zero term here of the sum will be curly P 22 curly P 33 J23. Now curly P22 and curly P33 are both minus 1, so you get 2 minus 1 factors, but 2 minuses make a plus. As a result, this is exactly equal to J23. Now this will happen whenever you have 2 spatial indices. It's pretty easy to see that. If you have 2 distinct spatial indices, I and J, you're actually talking about an angular momentum component. And there, because of these curly P's, you're going to pick up 2 minus signs, and that means that the spatial component of J mu nu, that is a Jij, will not change under this kind of a transformation. On the other hand, as far as boost is concerned, if you start with J0i, let's say J01 in particular, P J01 P inverse, according to this, is going to be curly P mu 0, curly P nu 1 J mu nu, and curly P mu 0 has only one non-zero term, which is curly P 00. Curly P nu 1, as you run over nu, has only one non-zero term, curly P 11. But now you have 1 plus 1 from curly P 00 and a minus 1 from curly P11. That is, an overall minus sign comes about. That will happen whenever you have one temporal and one spatial index. You will get exactly two non-zero curly P elements, but one of them, the 0, 0 element, will be plus 1. The other element, the purely spatial diagonal element, will be minus 1. So you will have a change of sign. Now, capital P, capital H, capital P inverse is something we have already seen has to be equal to capital H. In fact, that's what helped us to decide that capital P is a linear unitary operator in the first place. So what we are now interested in is what happens to spatial indices. Capital P, P1, P inverse. Now that's curly P mu 1, P mu according to this rule, and that again tells you that the only non-zero term in the sum is curly P11, P1, and because of the sign of curly P11, this is going to be equal to minus P1. So momentum components will change sign. Not just P1, P2 and P3 will have change sign in exactly the same manner. Now what about capital T? Capital T essentially follows along the same lines, except that when you apply capital T transformation on J23, for example, you get capital T J23 T inverse is minus, this is an extra minus sign which comes from this minus I coming out of the anti-unitary capital T. And then you have curly T mu 2, curly T nu 3, J mu nu. Once again, curly T is diagonal, so there's only one non-zero term. And now, both of these two terms are plus 1, but there is an overall minus sign, so you end up with minus J23. So angular momentum changes sign under time reversal. Well, what about boost? You start with capital T J01 T inverse, you carry out exactly the same kind of calculation. The extra minus sign that you have in the front will actually give you a plus overall, so you are going to get plus J01 as a result, instead of minus J01 as you had in the case of parity. So as far as Lorenz generators are concerned, parity and time reversal produces opposite effects. As far as momentum is concerned, on the other hand, capital T P1 T inverse will be simply minus curly T mu 1 P mu, and that means it's going to be minus curly T 1 1 P1, and that is simply equal to minus P1. So both parity and time reversal change the sign of momentum components. Now, although we wrote this down for specific angular momentum boost or momentum components, it's pretty easy to put them all together and write down these general relations. Capital P, J vector, P inverse, is going to be just J vector. Angular momentum is not going to change under parity. Now that is something which we know from classical mechanics. Angular momentum, after all, is a cross product of two real vectors. It's thus a pseudo vector, and under parity, both the real vectors r and small p, position vector and momentum, change sign, but the angular momentum doesn't. Under time reversal, on the other hand, r does not change sign, momentum does, so their cross product changes sign. So T inverse actually changes sign, which is consistent with that. P, capital P, K, P inverse changes sign to minus K. T, capital K, T inverse, on the other hand, does not change the sign of K at all. It gives you back plus K. Once again, it's easy to figure out what the result will be for the final set of transformation equations. Those for momentum. Momentum being a real vector changes sign under parity. That's exactly reflected by our operator equation. Capital P, P vector, capital P inverse is minus P vector. And of course, time reversal essentially means running a movie in reverse. So capital T, P vector, T inverse is minus P vector as well. Now that we have these transformation equations for the angular momentum boost generators and momentum operators, a concern that could be raised is the following. We already know of commutation relations between these operators J, K and P vector. Are these transformation equations consistent with those commutation relations? So just to check, let's start with the most familiar commutation relation of them all, the commutation relation between the angular momentum components Ji and Jj. And as you all know, this is exactly equal to I epsilon I jk, jk. Now, if we hit this equation from the left by P and from the right by P inverse, what we get is the following. Now, it's easy to see that P times the commutator of AB with P inverse, where P can stand for any invertible operator now, is exactly the same as a commutator between PA P inverse and PB P inverse. All you have to do is to expand out both sides and this will be self-evident. So our relationship with parity operator and the angular momentum components simply becomes P Ji P inverse commutator with P's Jj P inverse. Now this should be equal to, on the right hand side, the following: I epsilon I jk P jk P inverse. Now according to our transformation equation, P j P inverse is the same as J. So what the left hand side simply becomes is Ji's commutator with Jj. And the right hand side simply becomes I epsilon I jk times jk, which is exactly consistent with our original commutation relation. So this particular transformation equation is definitely consistent with the way the angular momentum operators commute with each other. Well, what about the time translation transformation, time reversal transformation, capital T J, T inverse is minus J. Now, if we did the same thing with capital T, all we would have to do is change these P's to T's, and you would get T Ji Jj T inverse equals T I epsilon I jk, jk T inverse. Now, carrying out the same steps as before, what I would get is the commutator of T Ji T inverse with T Jj T inverse is I epsilon I jk with a minus sign. Remember, T is anti-linear, so I coming out of that would change the sign of I. T jk T inverse. Now note that our relationship that Tj T inverse is minus J is exactly consistent with this, because if I replaced the Tji T inverse and Tjj T inverse on the left hand side with minus Ji and minus Jj respectively, I would get two minus signs from the product, and that will give you the same as the commutator Ji Jj on the left hand side. On the right hand side, you will get I epsilon I jk times minus jk here, but with this minus sign, you will get a plus overall, and you will get back the original commutation relation. So, it is the anti-unitarity of T which saves the day here and gives us the extra minus sign which is needed to keep the relationship consistent with our original commutation relation. You can easily check that the same thing happens for the other commutators, like the commutator between J and K, or between J and P, or between K and P. So I will leave that as an exercise for you to work out. Now, let me just end by saying that these relationships that we have derived so far make perfectly good sense. We have now acquired all the machinery that we need to talk about the way in which four momentum eigenstates for single particles would transform under parity and time reversal. We are next going to turn to that particular topic. We will begin by talking about the way in which massive particle states transform under parity and time reversal, and then go on to talk about the way in which massless particle states transform. But all that is for the next parts of this lecture. Bye until then.